Now, we study another criterion, which is very important for for establishing the convergence, divergence of improper integral of functions with a sign that changes, and the theorem is the following. It is called the criterion of the asymptotic behavior. So again, you have a function f from an interval, a half-line a plus infinity to r, that is integrable in every interval AC, with C larger than A, and f of x equivalent to L x to the minus alpha for x going to plus infinity, with L in R minus 0. L is whatever real number, but it is not vanished. Then, if alpha is larger than 1, then the integral between a and plus infinity of f converges, and for alpha not larger than 1, then the improper integral of f from a to plus infinity diverges. So what is the message? Is that the improper integral has the same behavior of the improper integral of a prototype which is equivalent to the integrand, provided that it exists. And now let us go with a proof. The starting point of the proof is a nostalgic one, because I say let epsilon larger than 0, like in October. So now the fact that f is equivalent to Lx minus a for x going to plus infinity, this means that x to the alpha f converges to L as x goes to plus infinity. This means that there exists some x bar not smaller than a, such that L minus epsilon less than x to the alpha f less than L plus epsilon for every x larger than x bar. This is just the definition of limit. Then L minus epsilon divided by x to the power alpha is less than f, less than L plus epsilon divided by x to the power alpha for every x larger than x bar. Now there can be some problem of sign in the case that epsilon here changes the sign of L, or also here if L is negative. So in order to be coherent with the theorem for improper integral with constant signs, we say that epsilon must be less than the absolute value of L. So if this is true, then L minus epsilon, L, and L plus epsilon has the same sign. Have, because they are three, have the same sign. So, if alpha is larger than 1, then the first case is L larger than 0 implies L plus epsilon divided x to the power alpha larger than 0, and L plus epsilon divided by x to the power alpha, improper integral from a to plus infinity, is convergent because of the study of prototype. Then, by the comparison criterion, the integral, the improper integral from a to plus infinity of f converges. Second, if L is less than 0, then the integral from a to plus infinity of L minus epsilon divided by x by alpha dx is larger than minus infinity. Then we use the same criteria for positive functions to be improperly integrated. So we reverse them for negative functions, and here we see that here we have a function which is negative, whose improper integral is not negatively divergent. Then, again, by comparison criterion, and the study of prototypes, and adapted to the case of negative, of non-positive functions, we can conclude that the integral between a and plus infinity L minus epsilon divided by x to the alpha dx is f of x f of x dx converges. And then the other case, here we discussed the case of convergence, alpha larger than 1, and then finally, if alpha is not larger than 1, then first case of positive L, then we have L minus epsilon over x to the alpha larger than 0, and we have divergence here of this integral. By comparison, from the other side, since this integrand is not larger than our function to be integrated, and then we conclude that the integrand between a and plus infinity of f of x dx is equal to plus infinity. Second, L less than 0, then L plus epsilon divided by x to the alpha less than 0, and integral between a to plus infinity I plus epsilon divided x to the alpha dx is equal to minus infinity. And by comparison, again, we conclude that the integral between a and plus infinity of f of x dx, this improper integral, negatively diverges. And this is the end of the proof. This proof is extremely simple, but this is because here we have L non-zero. Of course, in order to write down an equivalence, you need that L is non-zero. If L is equal to 0, everything is 0, so it is very simple. But the point is that L is positive or negative, so eventually for x going to plus infinity, the function f, to be improperly integrated, has a definite sign by permanence of sign. So we fall again to the first class of functions to be integrated, the functions with constant signs, and they are easier. And so as an exercise, a nice exercise to be done here is the following. So the question is, for which values of alpha the improper integral between 0 and plus infinity of pi over 2 minus arctangent of x to the power alpha converges. Oh, this is a question I already gave you this question when talking about principal parts, and again, it is not possible for us to perform properly this exercise, because we need, in order to do that, we need the L'Hopital theorem. Okay, so we have to do it next lecture. Next lecture we will start with the L'Hopital theorem. So let us go to the second type of improper integrals. So second type of improper integrals. Which means integrals of unbounded functions defined on bounded intervals. A picture can be this one. And here you have an interval A, B. You want to compute this area, and so the trick is again the same idea. You take a C here, and you define this integral function f of c is equal to the integral this time from C to B, so we exclude the asymptote here, and f of c is equal to the integral between C and B of f of x dx. And so I will go quite fast here because it is really analogous to what we did up to now. And so the first definition says that there are three cases. The first case, 1, the limit for c going to a plus of f of c exists and is finite. Then the improper integral of f between a and b, so in the interval ab, converges. So, and one writes integral between a and b of f of x is equal to the limit for c going towards a from the right side of the integral between c and b. So notice that here in the notation, you lose any track of the fact that this is improper. The improperty, so to say, of the integral is encoded in the function. You have to detect the singularities, the asymptotes. Okay? And second, if the limit, same limit for c, going to a plus of f of c, is plus infinity or minus infinity, then one says that improper integral of the function f in AB diverges positively or negatively. So I use the parentheses, I use the brackets, so I keep on using the brackets. Third, if the same limit again does not exist, then the improper integral between a and b is indeterminate. Again, you have a collection of prototypes, which is very important. But this time, prototypes show singularities 1 over x minus a to the alpha, so singularity in a, and the integral function we defined before is the integral between c and b of dx divided by x minus a to the alpha, and is equal to x minus a to the power minus alpha plus 1 divided by minus alpha plus 1 between c and b for alpha different from 1, and of course, as usual, logarithm. Again, x is larger than a, so we can get rid of the absolute value and take brackets for alpha equal to 1. So this is equal to, just evaluating the primitives, b minus a to the power minus alpha plus 1 minus c minus a to the power minus alpha plus 1 divided by minus alpha plus 1 for alpha different from 1, and log of b minus a divided by c minus a alpha equal to 1. So for alpha different from 1, this quantity here becomes b minus a, sorry, I rewrite it. So b minus a minus alpha plus 1 minus c minus a to the power minus alpha plus 1 over minus alpha plus 1 tends to a finite quantity that I write here, minus alpha. Notice that here when c goes to alpha, and here this quantity is positive, so when alpha is less than 1, this term here goes to 0, otherwise it goes to, for alpha larger than 1, this goes to plus infinity, then minus infinity, but then the denominator is negative, so we end up with plus infinity. Okay? And for alpha equal to 1, we have that log of b minus a divided by c minus a, tends to plus infinity for c going to a plus. Here too, of course, it was the limit for c going to a plus. So, as usual, therefore, the integral between a and b of our prototypes converges if alpha is less than 1 and diverges otherwise. So an important remark which is useful for memory is useful for exercises, says that the role of the prototypes is reversed with respect to the improper integrals of the first kind. So, of the type a plus infinity dx over x to alpha, except, be careful here, for alpha equal to 1, where in all cases, for all types, divergence occurs. So, but however, so example. Quite important. Let's discuss the convergence of the integral from 0 to plus infinity dx over x to the alpha. So here there are two sources of improperty. The singularity at x equal to 0 and the fact that the integral is on a half line. Now we have to discuss separately. I have to stress here, discuss separately and independently the two sources. And then if only one of them gives divergence, then the integral diverges. In order to have convergence, you have to show convergence for every source of singularity. And so in order to separate the two sources of singularity, you have to separate 0 from plus infinity by intertwining another point, for instance 1, but you can choose whatever positive number you like. And then you can do a table here for, you can write a table here for the two of them. And here you have, for instance, alpha larger than 1. And you have that the first integral from 0 to 1, this goes to plus infinity. This is finite. So the result is plus infinity. For the second, alpha less than 1, this is finite. This is plus infinity. But here you have plus infinity, and then you have again for alpha equal to 1. And in this case, in both for both integral, you have plus infinity, so you have divergence. So the conclusion is that this integral diverges for every alpha. And then for the rest, you have the same criteria that we already discussed for the other type of integral. So the criteria of convergence are the same. The first was comparison. It is the same. So if you have f less than g for every x in AB, then if the integral from a b of f dx diverges, then the integral a and b of g dx diverges. Oh, sorry, here you have to put 0, otherwise it is not true. And here the integral from a and b of g converges, then also the integral from a and b of f converges. And then you have second, absolute convergence. For the absolute convergence, you have, again, if a and b absolute value of f converges, then also the integral of f converges, and the vice versa is not true. And the last one is the asymptotic comparison. So if you have that f of x is equivalent to some prototype for x going to a plus, then if this alpha is not smaller than 1, then this quantity diverges. And if alpha is less than 1, then this quantity converges. Again, almost the contrary with respect to the previous case. And as a final exercise, I suggest you to think of this. Establish the behavior of the improper integral 0 up to plus infinity to the minus x hyperbolic sine of x divided by square root of absolute value of x minus 3. Here you have the log of hyperbolic cosine to the power minus 3 over 2, and here absolute value of sine of x over 2/3. Notice that this integral is impossible to be computed. It's very difficult to be computed explicitly. Okay, but the exercise is just on establishing this behavior. So the integral is improper. You have to collect all the reasons why this integral is improper and to discuss them independently, separately. So the integral is improper since first, it is on 0 plus infinity. Second, the integrand diverges at 0, perhaps, or seems to diverge at 0, I don't know. It depends, because there is also hyperbolic sine, sine of x 2 over 3, so we have to investigate whether it diverges. 3. The integrand diverges at 3 from the left, and the integrand diverges at 3. at 3 plus, and stop. So here we are. And so the exercise is to discuss all of these sources. Should I do it? It is too complicated. Okay, I do it. First, let us go for the second, for x going to 0. We have many things to be discussed here. Here you have e to the minus x, hyperbolic sine of x divided the square root of the absolute value of x minus 3 times log hyperbolic cosine of x to the power minus 3 over 2 divided sine of x to the power 3/2. So this is equivalent to what? Here you have a constant, so this is 1 over square root of 3. The exponential goes to 1, so you remain here with sine of x, hyperbolic sine of x, divided by sine of x to the power 2 over 3. And here, log hyperbolic cosine minus 3 over 2. Now here, the first factor to be examined is hyperbolic sine of x divided sine of x to the power 2 over 3. For x going to 0, this is x, hyperbolic sine of x, this is x to the power 2 over 3. So this is x to the power 1/3. So this factor gives no problems. So it is not divergent. And let us see the other one. If you have logarithm of the hyperbolic cosine of x, write it as the logarithm of 1 plus hyperbolic cosine of x minus 1. This is equivalent, because this goes to 0, this is equivalent to the hyperbolic cosine of x minus 1, and this is equivalent to x squared over 2. Therefore, the hyperbolic cosine of x put inside the logarithm and to the power minus 3/2, it was with another bracket here, this is important. This is equivalent to x squared over 2 to the power minus 3/2. So it is equal to x to the power minus 3 divided by square root of 8. An important fact is that then at 0 the behavior is hyperbolic cosine of x divided by, let me copy all the function to be more precise. So this goes like 1 over square root of 3, x to 1/3, x minus 3 to square root of 8. So this is 1 over square root of 24, and x to the power minus 8 over 3. And here 8 over 3 is less than 1, so the improper integral diverges at 0 by prototypes. So it is finished. This integral diverges. So the exercise is finished already. But, okay, because it doesn't matter what happens at 3. We already have a source of divergence. However, as a training, we can analyze the other singularities. So for x going to 3, we have 3 and 4 here. We have e to the minus x, sorry, let me again write down the whole function. Here we have e to the power minus 3, hyperbolic sine of 3, sine of 3 to the power 3 and 2/3, log hyperbolic cosine of 3 to the power minus 3 over 2, no problem, and then square root of x minus 3. This goes as c divided by absolute value of x minus 3, which means c over square root of absolute value of x minus 3 for x larger than 3, and c divided by square root of 3 minus x for x less than 3. In both cases, alpha is equal to 1/2, which is less than 1, then such a singularity alone would not give rise to divergence of the improper integral. And then the final source is to plus infinity. Let us see what happens. Okay, this is easily done. I leave you, so as a homework, discuss the case x to plus infinity. And then another type and this is another class of improper integrals where you have a discontinuity but not an asymptote. So you have the integral from 0 to 1 of sine 1 over x dx. And this you can easily solve this exercise by a trick, by this change of variable, which is quite natural. So this is turned on into a true improper integral. And we know that this absolutely converges, so it converges. Remember that here the idea is to sum up the areas here. Here you have a nice function like this, but then it becomes completely crazy around 0. And you have to sum infinitely many small areas. And another exercise similar to this is this famous Frenet integral, sine of x squared dx. This is called Frenet integral. But another exercise which is very interesting as a homework, also this one I leave you as a homework, that says find a positive function f, so such that it is false that f of x goes to 0 for x going to plus infinity, and the improper integral is convergent. And this is the end for what concerns improper integrals. And now we will go back to local analysis.